Have you ever wondered how propofol, commonly known as Diprivan, works so effectively as an anesthetic? Let's explore the structure-activity relationship of propofol to understand how its chemically structure influences its function. Propofol's chemical name is 2,6-diisopropylphenol. Its structure consists of benzene ring with two isopropyl group at position 2 and 6 and a hydroxyl group. Each component plays a crucial role in its anesthetic properties. At the core is the phenyl ring. This structure is essential for interacting with the GABA A receptor in the brain, enhancing inhibitory neurotransmission and leading to sedation and loss of consciousness. Attached to the ring are two isopropyl groups at position 2 and 6. These bulky groups increase the molecule's lipid solubility, allowing propofol to rapidly cross the blood-brain barrier. This characteristic contributes to its quick onset of action, typically within seconds. The hydroxyl group contributes to the molecule's solubility and may influence its interaction with receptors, although its role is secondary compared to the isopropyl groups. Upon administration, propofol lipophilicity ensures swift distribution in the brain. By binding to GABA A receptor, it enhances the inhibitory effects of GABA, leading to the desired anesthetic effects. In summary, propofol's effectiveness as an anesthetic is attributed to phenyl ring for receptor binding, the 2,6-diisopropyl groups for increased lipid solubility and rapid brain penetration, and the overall enhancement of GABA A receptor activity. Understanding the structure-activity relationship of propofol sheds light on its efficiency and rapid action as an anesthetic. This knowledge is crucial for developing safer and more effective anesthetic agents.
Ketamine's structure-activity relationship provides insight into how structural modifications affect its pharmacological properties, particularly anesthetic, antidepressant, and dissociative effect. Ketamine works like a special key that fits into the locks in the brain called NMDA to help with pain, sleep, or sadness. Ketamine's SAR is influenced by its aryl cyclohexylamine core with K structural features affecting its activity. So 2-chlorophenol group is essential for NMDA receptor antagonism, changes reduce potency. So it's like the head of the key helps the key fit into the lock. Changing its shape makes the key not work as well. Then, cyclohexanone ring is crucial modifications weaken activity. The secondary amine influences binding and alkylation, affects lipophilicity and duration. So, it's like the tail helps the key turn the lock. Adding or taking parts of the tail can make the key work longer or shorter. There are left-handed keys or the S-ketamine and right-handed keys the R-ketamine. So the left-handed key works faster but the right-handed key helps with sadness longer, or it has a longer antidepressant effects. Bioisosteric changes, for example, replacing ketone or modifying the ring, reduce activity.
Good day, ma'am. Today, I'm gonna report the structure-activity relationship of halothane, which is an example of an anesthetic drug. So what is halothane? Halothane is a halogenated inhalational anesthetic. It is a volatile liquid with a sweet odor and historically used for general anesthesia. But due to the risk of hepatotoxicity, its use has declined in favor of safer alternatives. So what is the mechanism of action of halothane? So halothane induces general anesthesia by acting on multiple ion channels, leading to central nervous system depression. It primarily enhances GABA A receptor activity and it affects potassium channels in cholinergic neurons, contributing to its immobilizing effects. So this results in decreased nerve conduction, respiratory depression, and reduced cardiac contractility. So now I'm gonna explain the structure-activity relationship of halogen. So first is the halogen substituents. So the presence of bromine and chlorine atoms is essential for enhancing the anesthetic potency. These halogens increases the lipophilicity of the molecule, facilitating its action in the lipid-rich environment of the central nervous system. Second is the trifluoromethyl group. This group contributes significantly to both the anesthetic potency and stability of halothane. The fluorine atoms enhance the hydrophobicity and reduce metabolic reactivity, decreasing the risk of toxic metabolites. The third is the absence of double bonds or aromatic rings. Halothane lacks double bonds and aromatic structures, which minimizes the potential for toxic metabolite formation during metabolism, making it safer for clinical use. The fourth and last is its molecular size and shape. So, the size and shape of halothane allow efficient passage through the blood-brain barrier or the BBB, a critical feature for inhalational anesthetics. So, in conclusion, halothane's anesthetic properties are largely influenced by its halogenated structure, which enhances its potency, lipophilicity, and metabolic stability. However, due to safety concerns, its clinical use has significantly declined.
Next is lidocaine. So first, let's start with the MOA of the lidocaine. Lidocaine works by blocking sodium channels in nerves, which stops them from sending pain signals. This makes it an effective local anesthetic. It also helps stabilize the heart's electrical activity when used for heart conditions. Next is the SAR of lidocaine, or also known as the structural activity relationship. So, the structure-activity relationship of lidocaine involves key parts. First, we have aromatic ring. It helps the drug cross cell membranes and binds to sodium channels in nerves. Second, we have amide group. It connects the aromatic ring and alkyl chain, making lidocaine stable and effective. Third, we have alkyl chain. It helps lidocaine interact with sodium channels to block nerve signals. Fourth, we have amino group. It ensures lidocaine works properly in the body by changing its charge in different environments. These parts together allow lidocaine to block pain signals and work as an anesthetic.
Hello everyone, my name is Nicole Shea Makato and I'm here to explain the mechanism of action and structure-activity relationship of fluorine or isoflurane. Mode of action. Isoflurane works by directly interacting with neural membrane in the brain, disrupting the transmission of nerve impulse. This leads loss to consciousness and general anesthesia. Isoflurane enhances the effect of GABA, an inhibitory neurotransmitter in the brain. This further contributes to the CNS dispersion and anesthetic effect. Isoflurane also reduces the excitatory effects of glutamate, another neurotransmitter in the brain, thus further enhance the overall anesthetic effect. The structure-activity relationship or SAR of fluorine or isoflurane is isoflurane structures includes the halogenated ether group, which is essential for its potency and rapid introduction of anesthetic. This structure allows for efficient penetration of the blood-brain barrier, reaching the target sites in the CNS. The specific arrangement of fluorine, ether, and alkyl groups is isoflurane structure, contributes to its potency as an anesthetic. The presence of fluorine and the ether group contribute isoflurane rapid introduction of anesthetic and smooth recovery. The SAR of isoflurane also explains some of the side effects such as respiratory depression and potential for trigger malignant hyperthermia.